So this is the emergent ray. It must actually be parallel to the incident ray. So refracted rays are indicated by these arrows. Very, very, very important. So we are to determine the extent to which the original ray is displaced from the emergent ray. So this distance is what we are to calculate for displacement. Don't also forget that the same distance can also be measured from this point to this point. Joshua.
Sir, please, good afternoon.
Yeah.
Sir, please, there was power outage in our area, so I could not join the class early, so I don't understand how you drew the diagram.
We've just started. We are revisiting the assignment I gave you, okay?
Okay, sir.
All right.
Thank you, sir.
Welcome. So this is the refracted ray. This is the emergent ray. This becomes the angle of refraction. And what we have here is the angle of deviation, okay? Last time when we went through, okay, for the benefit of those who were not around, let's go through again to get how we determine or we got that relation. So supposing this is point O, A, B, and then C. This side is perpendicular to X, Y, W, Z. I'm just renaming the parts of the prism, okay? So the normal is perpendicular to the side ZW. Equally, the displacement is perpendicular to OA. So if we consider the right angle triangle OAB, OAB, and the angle of incidence, this is the angle of refraction. This angle here, triangle O, the angle there, let's indicate this as sigma, a symbol. So sigma is equal to the angle of incidence I minus the angle of refraction. So when we take sine of this angle, sine sigma, this is equal to AB over the hypotenuse OB. Class, I hope you are following. Are we following?
Yes, please.
So OB is equal to AB over sine sigma. And we can find sigma by subtracting IR from I. So I sine of I minus R. Let's consider the other triangle for the same analysis. Triangle OBC. OBC. This time we will take the cosine because we have the adjacent. And then, so cos of R, we have the adjacent, we have the angle, and we are looking for the hypotenuse OB. Cos of R would be OC over OB. So that when we make OB the subject, let's name this to be equation 1. OB the subject here, we have OB giving us OC over cos of R. And OC is 2 centimeters. So 2 centimeters divided by cos of R. And this is our equation 2. So because this is about AB, OB, and this is also OB, we can equate them. AB over sine I minus R is equal to 2 over cos of R. Okay, and AB is D. So let's substitute D in place of AB and make it as a subject. D will be equal to 2 times sine I minus R all over cos of R. Let me look at your messages quickly. Okay, I'll respond to it. Okay, I'll respond. Refraction of light in rectangle. Okay, so okay, somebody has answered. Yasmin just answered. Refraction of light in rectangular prism. Thank you, Yasmin. Now, our bone of contention is to find R because we have I. Okay, we are to find R. So using Snell's law, absolute refractive index is sine of I over sine of R. Okay, we're given the refractive index of the rectangular prism. And when you look at the sub question, okay, so class, what were we given as the refractive index of the prism? What were we given as the refractive index of the prism? Anybody?
1.5.
Okay, so sine 30 divided by 1.5. And sine 30 is equal to 0.5. So we have 0.5 divided by 1.5. Divide 0.5 by 1.5 for me. 0.5 divided by 1.5.
3.
Come again. Hello, come again. 0. Oh, who are those answering?
0.3. 1 over 3 or 0.3333.
Okay, so that recurring 3. Therefore, R would be equal to the sine inverse of what we had, 0.3333. And I guess this gave us 19 point something. 19 point, is it 5?
47.
Okay, 19.47.
Yeah.
A caution. In fact, when I was marking your assignment, I saw that most of you were running your values to their nearest degree. You see, yes, on the protractor, you can have points of angles. The least you can measure on your protractor is 1 degree. But you don't run your values to the nearest one here, especially when you'll be using it to calculate for another. At least 2 dp will do. If in your final answer presentation, you are running, that is better, but not when you'll be using the same value in calculating for another. Please, is that clear? Are we okay?
Yes, please.
All right. So having obtained R, we can calculate for the angle of deviation, which is also I minus R. I being 30 minus 19.47. What is 30 minus 19.47?
10.53.
10.53 degree. Then we can quickly calculate for D. So 2 times sine of 10.53 all divided by cos of 19.47. And this will give us, is it 0.38 class? Did we get 0.38 centimeter? So that is the answer for the first part, for the lateral displacement D. Can I continue? I want to move on to the next page. Are you done writing?
No.
Okay, please hurry up whilst I take attendance, okay? Do that quickly for me. I want to take attendance quickly.
Recording in progress.
Okay, so I'm sure you are done. Let's move on. The next question demands that we calculate for the time taken for the light to move through the prism. Obviously, time is equal to speed divided by, let's take it from this perspective. V is equal to D on T. So when you make T the subject, you have D on V. So this is, hello?
It seems you've paused your screen sharing.
Yeah, yes, I just saw it. Thanks. You are marking me boot by boot, okay? So T will be equal to D over V, meaning that we have to understand the distance traveled by the light and also the speed of the light within the prism. For speed of light, it's easier. Absolute refractive index is speed of light in divided by speed of light in the medium. So it means that V would be equal to C over the refractive index of the material. Speed of light in air and vacuum is constant. 3 times 10 to the power 8. Please, those of you who are fond of using 299, please run it to 3 times 10 to the power 8. Usually this constant must be given, but it should also be a known constant to disciples of physics. So you must know them. So V would be 3 times 10 to exponent 8 divided by 1.5, which I think would give us 2.0 times 10 to the power 8 meter per second. So we have the speed of the light in the prism. Then with regards to the distance traveled by the light, please, this width of 2 centimeters given is not the distance traveled by the light. Look at the diagram. This is the part of the refracted ray. The light is refracted at an angle. Let me use, so this is the part of the light within the prism. And so that must be the distance traveled by the light source. Okay, this must be the distance traveled by the light source. It means that to get the distance, we must find the hypotenuse OB. Okay, we must find OB. We can use any of the equations, either equation 1 or 2 to do that. So OB would therefore be equal to AB. AB is has been calculated 0.388 divided by sine of the angle of deviation, which is 10.53. Okay, please somebody to help me do this calculation. 0.388 divided by 10.53. Yasmin, Anita, Pepra, Augustine, and the rest of you. Gideon, please help me in the calculation.
2.123.
2.123 centimeter. Thank you so much. So we have D, we have V. Now, because V is in meter per second, it means we must change D, which is in centimeter to meter. And this is by dividing through by 100. So 0.02123 meter. Therefore, TS, this distance, divided by the speed of light in the medium, 2.0 times 10 to the power 8. And this must give us 1, 1, 2. So 2.12 divided by 2 times 10 to the power negative 10 seconds. What is 2.12 divided by 2?
Say, please,
1.06.
0.06, right?
Yes.
Okay. Negative this seconds, or 106 times 10 to the power negative 12 seconds. And in parentheses, negative 12 is pico. So 106 picosecond. But you can still leave your answer in this part is correct. This part is also correct. And if you could express it in parentheses, it's also a feather in your own cap. So this is the answer to the question. Are we okay? Yes, Gideon.
So please, can you go back to the previous slide? I want to see how the D was calculated there. 0.388 over. So you want to see, okay, sir. Okay, sir, thank you.
Can
So we
can
can
we
see.
move? Can we move on?
Yes, sir. Yes, sir.
All right. I'm reading a question for you to try. Please quickly put this down so we can all analyze and continue. A ray of light traveling inside a rectangular glass block. A ray of light traveling inside a rectangular glass block of refractive index root of 2 of refractive index root 2 this symbol of refractive index root of 2 is incident on the glass air surface is incident on the glass air surface at an angle of incidence of 45 degree. At an angle of incidence of 45 degree. If the refractive index of air is 1, or if the refractive index of air is 1, what happens to the ray under these conditions? If the refractive index of air is 1, what happens to the ray under these conditions? So the question is, what happens to the ray under these conditions? So quickly, 5 minutes, work through it and let's see what your conclusion will be. I'm going over the question. A ray of light traveling inside a rectangular glass block of refractive index root of 2 is incident on the glass air surface at an angle of incidence of 45 degree. At an angle of incidence of 45 degree. If the refractive index of air is 1, what happens to the ray under these conditions? What happens to the ray under these conditions? That's your problem of the day. Please start with 5 minutes. Please check if you haven't muted, do so for me, okay? Asada, mute yourself. Please, 5 minutes and try and then work within the time given. I beg you. 2 minutes. 2 minutes more. Francis, obey, mute yourself. 2 minutes more. Obey.
Yes. Yeah, no, I don't know. I didn't understand. Let's see my opinion.
Are we through? Class, are we through?
Class, are we through?
Sir, please, where can I get this topic?
Or refraction of light
Or
in
refraction of light in
rectangular prism.
rectangular prism. Okay.
Check and refraction of light.
And refraction of light.
So we have
Okay.
refraction.
So we have refraction.
And then refraction of light in rectangular
refraction of
prism,
light in
triangular prisms, and
triangular
then
prism.
and refraction in lenses. Okay.
Sir, but I can't find it too.
Which book?
Which book?
Ataki.
Oh, it must be there. Either
Or it
in
must be
book 1
there.
or book 2.
Either in book 1 or book 2.
Don't forget
Okay, then
Atake.
maybe.
Don't forget Atake.
Yes, he was using the old syllabus, so it wouldn't follow that orderly.
Okay, then maybe it will be in the book 2.
Yeah, and the light.
Yeah.
Okay.
Because in the book 1,
Light.
okay, because in the book 1 I can't find it.
All right.
All right.
I'll also check and then update you.
Okay, sir.
Gideon, are you done?
So please, I think so.
So what happens to the ray under these conditions, Gideon?
So please, under the conditions given, the ray will be refracted through an angle of 29.99 degrees and be deviated through an angle of 15.01 degrees.
Okay, so that is what Gideon has. Let's hear from 1 or 2 so we can generally discuss it. Anita, what happens to the ray under the condition? Anita or Yasmin? Ablina, hey, Augustine, aren't you through with what you are supposed to do? Okay, Saki. Saki, let me hear from you.
So please, under the conditions, it will refract with an angle of 30 degrees.
So the angle of refraction, the thing will be 30 under this condition.
Yes, sir.
The ladies, let me hear from you. Yeah, it's the ladies. Anita. Yo, okay. Yasmin, are you there? Yasmin, Ablina, you also here?
Yes, sir.
What happens to the ray under this condition?
Yes, so it refracts with an angle of 30 degrees.
Okay, let's see. Let's see whether all the answers. Elikem.
Sir, please.
Yeah.
Because the refractive index of air is 1, and that of the glass block is √2. You find the critical angle, and the critical angle is 45 degrees, and because the incidence ray also hits the surface at 45-degree angle, the ray that is supposed to refract, it will be at the surface of the glass block.
In fact, let's clap for Elikem. Class, let me hear you clapping for Elicum. 3 points. Elicum, if they will not clap for you, just clap for yourself. So that is what will happen. The ray will be refracted, and the refracted ray will be on the boundary between the two media, meaning that the angle of refraction in this case is equal to what? The angle of refraction is equal to, meaning the angle of refraction in this case is equal to.
Davis, can you repeat what you were saying?
You see, the angle. Okay, so let's calculate. We have the refractive index of the glass block to be √2, and refractive index of air to be 1. So if we are also told that it's a ray of light traveling inside the rectangular glass block of refractive index that is incident on the glass air surface at an angle of incidence of 45. So I is 45 degree. So if we go by the product of the refractive index of glass and the sine of the angle of incidence is equal to the product of the refractive index of the second medium, which is air, then the sine of the angle of refraction. Okay, this is √2, this is 45, and in this case, assuming we don't know the angle of refraction, R, so √2 times sine of 45 will be equal to the refractive index of air, which is 1, times sine of R. And sine 45 is √2 on 2. Is equal to sine of R. Therefore, we have sine R being equal to 2 on 2. Because √2 times √2 is 2. So this is 1. Therefore, R will be equal to 90 degrees. So if light passes through a glass prism and the angle of refraction is 90, class, what does this tell you? If light passes through glass prism and the angle of refraction is 90, what does it mean? It means that you have the angle of incidence being equal to the critical angle. So it means the critical angle of the glass is 45 degrees, equal to the angle of incidence. And we learned that when the angle of incidence is equal to the critical angle, the angle of refraction will be equal to 90 degrees. So under this condition, the refracted ray will be on the boundary between glass and air. That is the answer. Janelle, are you there?
Yes, please.
Okay, Gideon, I'm listening. Okay, Saki.
You said you see to be on the boundary because the critical angle is 45 degrees.
The angle of incidence is equal to the critical angle. And in total internal reflection, whenever the angle of incidence is equal to the critical angle, the refracted ray is on the boundary and the angle of refraction is 90. Are you okay?
Yes.
All right. So that is the solution to this problem. Take note of this question. I'll be sending it to your teachers. Okay. Is there any question? No question. Let's look
So
at.
we can go back. I want to take a screenshot of it.
I'm recording also, don't worry.
So please, I'm done. Thank you.
Okay. Yes, there is this thing I need to also explain to you under real debt and apparent debt. You recall that when we look at a glass, a coin placed in water or under a glass prism, we've gone through this, but I think I need to teach you how to derive that refractive index formula and not to give that to you, because this time it's more of application thing. So if this is a coin or a spot, okay, under a glass block or water in a beaker, so let's consider this to be a coin or a spot. So if an observer is here, how will the observer see the image? So last time we saw that whenever a ray from an object, the rays must come from the object. And the ray is such that it is perpendicular to the surface. The ray goes undeviated. So a ray of light from the object traveling in this perpendicular manner would go undeviated. So this is the first ray. The arrow must be from moving from the object. Now a second ray from the object, which is at a different angle, would be so a second ray from the object moving from the object into air will be deviated, because this time it is at an angle. So if this is the normal is actually abnormal a little bit. If that is the normal, the ray would bend away from the normal to the observer. And will bend away from the normal because it is moving from a dense medium to a less dense medium. So when we trace back the original part of the refracted ray, we realize that it appears to intersect with this ray at this point. So it would appear to make that intersection at this point. We discussed this last time. Okay. Now we are going to use this to understand how we got the refractive index thing to be real dead over the apparent dead. Now the distance from the top to where the object is, we said this is the real dead, RD. The distance from the top to where the image appears to be, we said this is the apparent dead, AD. Now for the sake of our analysis, let me create points. Let's name this point to be point O. This is the image, so point I, point A, and then point B. Now, the ray is perpendicular at this point. Let me clean certain things. That ray line interference is actually disturbing me. Okay, good. Okay, so this is the angle of incident from the normal to the incident ray. So this is I. This is the angle of refraction, R. And by corresponding angle rule, we see that this angle, is it, I think, yeah, they correspond. The angle of refraction is the same as this angle, R, because they correspond. Class, do you see it? If this is R, this will also be R. Are we okay with that? Ladies and gentlemen, are you okay? Give me a feedback.
Yes, sir. Yes, sir. It's okay.
Okay,
So, we have a question.
quick one.
So, the angle from the point of where the apparent depth image will be formed, where the ray the blue one. So, is that angle between the blue line and the pink one, the pink line? What would the angle be? So, what would the angle be?
Is it this?
So, please no. So, is it forming a right angle
No,
triangle?
I get what you are saying, but I get what you are saying, but we are not so much interested in that angle now. Okay. So just let's understand I and R. So this is at the angle of incidence from the object to this ray. This is by corresponding angles. This R is equal to this. You don't forget about this first, okay? That is not what we'll be using for our analysis. So I just want to clear this so that the diagram will be neat. Oof, I'm coming for our use. Okay, Biny, quick one.
Sir, please, why is that the refracted ray, the angle there, at where the image is? I don't understand why that place is called the angle of refraction.
Oh, you see, the angle of refraction is the angle from the normal to the refracted ray, and this is the refracted ray. But we see that by corresponding angle, okay, if you extend this line angle corresponds with what is here. That is why this is R and this is also R. So we figured that out using corresponding angle rule. Banya, are you okay?
Yes, sir.
Okay, so we seem to have two right angle triangles. We have the triangle, please open your eyes, ABI. ABI.
Just like that, yes.
Please mute yourself if you haven't. Then we have another right angle triangle, ABO. ABO. Okay. ABO is the bigger one. ABI is the smaller right angle triangle. Class, I hope you are okay with these two triangles. Are we okay? Now, let's find sine of the angle of incidence I. Sine I will be equal to AB over OB. Please let me mute somebody. Okay, so sine I is AB over OB. Okay, then let's also look for sine of R. Sine R. Can somebody help me obtain expression for sine R? I've done so for I. Can somebody help me get sine R? Sine of R. Yes. Oh, let's not waste time.
The sine R is equals to AB on IB.
Good. So AB on IB or BI. Thank you, Yasmin. Let's also look for tan of I. Tan I. What will be tan I? Saki, Gideon,
Sir, please.
Yasmin.
Tan I will be IB all over OI.
Look at it again. Tan I. Tan I. Anybody? Let's not waste time, please.
The
Yasmin,
AB on
so AB opposite over adjacent. So AB on AO or OA. What about tan R? Tan of R. Tan of R. Saki. Alitia. Ablina.
AB over AI.
AB over good. So AB on AI. Good. Now, you see, the light is moving from denser medium to a less dense medium. So let's look at for the refractive index as light moves from water to air. The refractive index as light moves from water to air from Snell's law, a sine will be sine of I over sine of R. The refractive index as this light moves from more dense medium, water, into air, will be sine of the angle of incidence, which is I, over the sine of the angle of refraction, which is R. Are we okay here? So now, by small angles approximation, what we call as normal incidence, the angles I and R are considered to be very, very small. If I and small are very small, then it means that sine I would also be equal to tan I. And sine R will also be equal to tan R. So instead of sine I and sine R, we are using tan I and tan R. Tan I, we had AB over OA. Then tan R, we had AB over AI. Please simplify this for me. AB over OA, all over AB over AI. What will it be?
So
What will it?
AI over OE.
So the denominator would turn upside down. So we are going to have, let me go through this. So AB on OA times AI on AB. So this and this will cancel out, and the refractive index as light moves from water to air would be equal to AI on OA. Are we okay with this? Now, if you recall, if the refractive index as light moves from water to air is this, what will be the refractive index as light moves from air to water? Absolute refractive index. Yes. If from water to air is AB, what's the final answer? Okay, AI on OA. What will be the refractive index as light moves from air to water? Yes, Gideon.
So it will be OA over AI.
Exactly. We've done that. If you recall, product of the absolute refractive index and its reverse refractive index is equal to 1. So if from water to air is AI over OA, then from air to water will be OA over AI. Now from the diagram, what is OA? From the diagram, what is OA?
So this OA is the real depth.
The Ashima, please be talking. So OA is the real depth. Real depth. And then AI. What about AI? AI.
So this is the apparent depth.
Apparent depth. So class, that is how come we got the refractive index when an object or a spot is placed in either water or any liquid or glass block to be equal to its refractive index to be equal to real depth over the apparent depth. So this is how we got this. Now we were also talking about displacement, and recall that I said all measurements are taken from the surface of the liquid. So real depth must be taken from the surface of the liquid. Apparent depth must also be taken from the surface of the whether liquid or glass block. Now, so this remains the apparent depth. This is where the spot will be. And then this would also remain the real depth. How has the object's position been displaced? We got the displacement D, vertical displacement, to be equal to real depth minus the apparent depth. Okay, if you look at one of the information I sent you, I forwarded some notes on. Yes, let me repost it so you can see exactly what I mean. I mean this diagram. Yes, this diagram. We obtained a formula for displacement. What is the formula? D is real depth minus apparent depth. From this equation, please help me make apparent depth the subject. From the refractive index formula, help me make AD the subject. Anybody?
So this AD is RD over N.
So real depth over the refractive index. So if apparent depth is equal to real depth over the refractive index, then D can be expressed as, having factorized RD out, we have 1 minus 1 over the absolute refractive index of the material. So assuming the real depth is H, then the displacement will be h times 1 minus 1 over n. This is where this particular relation or expression comes from. Okay, in the notes, the displacement is termed as an apparent shift, which is equal to t. T is the real depth. T into bracket 1 minus 1 over mu. Instead of using nu, they use mu. Okay, so it's the same thing. So Ashima, if you ask, this is where this particular formula comes from. Please, are we okay? Are we okay?
Yes, sir.
Yes, please.
I'm going to forward another question to this effect so we can see how we can apply this in solving problems. I sent it to some of you to also try, but let me forward it to the group. Okay, so it's done. I've sent 2 questions. The first one says that the speed of light in air and water are 3 times 10 exponent 8 and 2.25 times 10 exponent 8, respectively. Calculate the critical angle for water when light travels from water to air. So you are given the speed of light in water, speed of light in air, and you are asked to find the critical angle of water when light travels from the water to air. I think this is not difficult, but before we solve this, please take note. Critical angle, if the less dense or rare medium is air, is given as sine C, which is equal to 1 over the absolute refractive index. Okay. Generally, if the less dense medium is not air, this is written as the refractive index of the less dense medium or rare medium divided by the refractive index of the dense medium. We've done this. Okay. So once we are told that the less dense medium is air, then it means we can use this. Equally, refractive index using speed is the same as speed of light in air or vacuum divided by speed of light in a medium. Meaning that if this is refractive index, then we can also say that then the critical angle would be equal to 1 over C over V, which in effect would be equal to V over C. Therefore, C is sine inverse of the speed of light in the medium divided by speed of light in air. So this is what we can use. Don't forget, we can also use wavelength. Wavelength, when light travels from air to the medium, is equal to wavelength of light in air over wavelength of light in a medium. Therefore, the critical angle can also be 1 over the absolute refractive index. If we substitute the nu into this formula, we have the critical angle being equal to 1 over lambda in air over lambda in the medium. Therefore, the critical angle will be wavelength in medium over wavelength in air. So all that I'm saying is that we can also calculate for critical angle when we are given speed of light or wavelength of light. You shouldn't always look at it from when it's only about angles. This is, okay, the explanation to the first question. So please finish it up for me. I've given you the tools you will need in doing this work. So please hurry up and then calculate the critical angle for me. So what's the answer? Sine inverse of 2.25 over 3. Hello? Yes, Alikem.
48.75.
So approximately 49. And I'm writing it to the nearest whole number because this is the final answer. Okay. All right. Please attempt the second question. Attempt the second question. Let me quickly read it to the whole class. It said an object is placed at the bottom of a basin at the bottom of a basin, and water is poured on it to a height of 10 centimeters. If the refractive index of water is 1.33, the object will appear to be displaced. The object will appear to be displaced by, so it means that you have to calculate the displacement. Okay, an object is placed in a basin and water is poured on it to a height of 10 centimeters. So assuming there's a basin, and then we have the objects, water is poured to the is poured within the basin to a height which is equal to 10 centimeters. If the refractive index of water is 1.33, what the object would appear to be displaced by. So I've taken you through this concept of vertical displacement. Please quickly determine that for me. 2 minutes. 2 minutes. Yes, Gideon. Okay.
So the displacement is 2.4.
Gideon, hello, Gideon. Let's wait for your other colleagues, okay?
Okay, sir.
So we can all get involved. Anna. Hello, Anna. Okay, so, okay, Anita, I've seen what you sent. So if you use this formula, displacement is equal to the height, real depth, which is 1 minus 1 over the refractive index of the liquid. The real depth is 10 centimeter. Then the refractive index is 1.33. This must give you 2 point something. Yes. Okay, 2.48. Somebody would want to go systematic. Instead of using the formula, somebody may be okay with, if the refractive index is real depth over apparent depth, then displacement is equal to real depth minus the apparent depth. Knowing that the real depth is 10 centimeter, all that it takes to solve for D is to find the apparent depth. So I make the apparent depth the subject. AD would be equal to real depth over the refractive index. The real depth is 10. The refractive index is 1.33. Please help me determine 10 divided by 1.33. 10 divided by 1.33.
0.133.
Check again.
7.5.
7.5.
7 point
519.
519. Therefore, the displacement will be 10 minus 7.519. And the results must be the same as what we got for this. I think you had 2.4 what? Is it 2.48?
Yes.
What's the answer here to 2 point? Okay, so that's it. So each approach is usable. Okay. Now, what if we have 2-3 different liquids and the object is placed under it? Example, we have 2-3 immiscible liquids. So these are 3 different liquids with different densities. So the density of this mu1, the refractive index of this mu1, mu2, and mu3. Please note that refractive indices also goes with densities. The depth of this is D1. The depth of the second liquid is D2. The depth of the third liquid is D3. Note that mu1 is less than mu2 and also less than mu3. Of course, when liquids are mixed, when 2 immiscible liquids are put together, the denser one must always settle below and the less dense one will be on top. So once we have this, it implies that the refractive index of the first one is the least. Okay. So if we have this kind of situation and a spot is placed here, how do we determine the total, the apparent depth, and then also to calculate the total displacement? So when you have a situation of this nature, you pick it liquid by liquid. So we know the absolute refractive index is RD over AD. So for the liquid one, what will be the apparent displacement? The apparent depth, it will be real depth, which is D1 divided by the refractive index of that liquid, N1. For the second liquid, its apparent depth, AD2, would also be its real depth, which is D2 divided by its refractive index. Then for the third liquid, AD3, it would be equal to D3 divided by the refractive index of the third liquid. Therefore, the total apparent depth, AD, would be equal to AD1, the apparent depth of the first liquid, plus AD2 plus AD3. What is AD1? AD1 is D1 over N1, U1, plus D2 over nu2, plus D3 over N3. This will be the total apparent depth of the spot placed under 3 immiscible liquids. Class, are we okay with this? Class, are we okay? We are going to apply this in solving problems. How then do I determine the displacement, the vertical displacement of the spot? D would be equal to D1. Of course, D is real depth minus the apparent depth. So the real depth is equal to D1 plus D2 plus D3 minus total apparent depth, which is D1 over N1 plus D2 over N2 plus D3 over N3. So this will be the solution to the problem. I'm giving you a question, an application to this. Please, I'm reading, so be attentive and then put that down for me. A rectangular glass block of thickness 10 centimeter. The thickness of the glass block is 10 centimeter. And refractive index equal to 1.5 is placed over a small coin. A rectangular glass block of thickness 10 centimeter and refractive index 1.5 is placed over a small coin. A beaker is filled with water. A beaker is filled with water of refractive index 4/3. A beaker is filled with water of refractive index 4/3 to a height of 10 centimeter. And is placed over the glass block. A. Find the apparent position of the object when it is viewed at the top. Find the apparent position of the object when it is viewed from the when it is viewed at the top. And B, find the vertical displacement of the object. Find the vertical displacement of the object. A, find the apparent position of the object when it is viewed at the top. And B, the vertical displacement. So class, this is your hot afternoon goodie. Problem of the afternoon. Start work.
Say, can you repeat the B again? The question.
The B question says that find the vertical displacement of the object. Find the vertical displacement of the object. All that the question seeks to test is that there is a coin placed under a glass block. This glass block has a thickness of 10 centimeters. Then a beaker is filled with water to a height of 10 centimeters and placed over the glass block. So it is basically glass and water. Okay, it's filled to 10 centimeters. So what will be the displacement? What will be the apparent position of the coin when viewed from the top? When an observer views from the top, what will be the apparent position of the coin? And when you finish, calculate the vertical displacement. So I think 3 minutes must be okay for this work. Start work.
Did you say the height of the glass box or the thickness?
No, the glass block was filled to a height of 10 centimeters. So from where the water level is, from the top of the glass block, we are told it is filled to a height of 10 centimeters. Are you okay?
Please, and that of the height of the beaker?
No, the height of the beaker isn't. Don't forget, this measurement will be taken from the surface of the liquid on the, okay, not the height of the beaker. Are you okay?
Yes, sir.
So the beaker is filled to a height of this. So it's as if the observer is viewing from exactly the surface of the liquid. So, and even if it's not, the eye level is above, it is within the same thing. So within air, so it will not affect it. Whilst you work, let me check. Cecilia, Abena, Akosia, Alexander, Amen, Anita, Aseda, Ashima, Esiedu, Fusuhene, Augustine, Barak, Caleb, Botche and Caleb Ufusu, Cephas, Daisy, Echo, Elikam, Elsie, hey, Elsie, Ernest, Frimpoma, Saki, Gerard, Gideon, Isaac, Isabella, Kennedy, Kenneth, Capicas, Kingsley, Joshua, Marilyn, Martin, Morris, Nana Kwame, Achia, Nana Kwame Osafo. Hey, When why you've not been talking, you've stopped talking. Ella, Nyamieni, you've stopped talking to Ohenebia, Sadem, Vanessa, Yasmin, Zainab, Zaratu, and Janelle. When Nyamieni, you people have suddenly stopped talking in class, which is not good. I'll tell your parents. 2 minutes more. 2 minutes more to end your work. I have this Nigerian question under the same thing, under the same concept we are treating. Nigeria, one of their physics questions. The year, I don't have it, but I have their question. I'll take a short. Gideon.
I'm done.
Okay. We'll discuss it, so don't worry, okay?
Okay.
I'm sending the Nigerian question on the platform. You can try it and then send me your solution later. Asada, are you there? Hello, Asada. The Nigerian question says that a piece of coin falls accidentally into a tank containing two immiscible liquids A and B, as illustrated in the figure 10.0. So we have liquid A and B. The depth or the height of A is 40 and B is 8. The coin is at the bottom of A. You have to calculate the displacement of the coin when viewed vertically from above. Take the refractive index of A to be 1.3, refractive index of B 1.4. So it's basically similar to what we are answering. Saki.
Yeah, it's okay.
All right. Please, have you found a question that the Nigeria question I just posted on the platform?
Yes, I think you have seen it.
Okay. All right. Let's try this. Let's try this one. So the first question asks that we find the apparent position of the object when viewed from above. So you pick it material by material. So supposing this is A and then B, the apparent depth of A will be equal to the real depth 10 divided by the refractive index of A, which is 1.5.
Bashira.
Then the apparent depth of B would also be the same 10 divided by the refractive index of B, which is 1.33. Therefore, the apparent displacement would be 10 over 1.5 plus 10 over 1.33. And if you got 14.2 centimeter, You can be smiling to the bank. Let me see by hands those of you who got 14.2. If you got 14.2, let me see you. Oh, okay. More hands. More truthful hands. So, okay. All right. Then the vertical displacement. The vertical displacement will certainly be the real depth minus the total apparent depth. The real depth is 20 centimeter minus 14.2. And that must also give us 5.8 centimeter. Okay. Then attempt the Nigerian question. Start work. Attempt the Nigerian question, which is just uploaded on the platform. Okay, Gablina, I've seen your answer. Attempt the Nigerian question. We have 10 minutes to end the lesson. Attempt the Nigerian question.
In progress.
Elsie. Elsie, can you hear me? Or Elsie cannot see. Gideon finished?
Yes, sir.
Okay. Who else is true? Yasmin is also true. Okay. Yasmin, I think your answer is correct. Gideon, what's your answer?
So please, I had 13.28.
For
So please,
that
for
calculated
the
displacement. I doubt.
so please for the
I doubt.
okay. Okay, so I'm taking it
Look
again.
at it again. There is another hand up. Ella. Ella, I'm listening.
So please, I had 11.56 centimeters as the displacement.
Okay, Saki.
So please, for the apparent depth, I got 36.48 and the displacement 11.52.
Okay, Janelle, let me hear from you. Hello, Janelle. Okay, Ablina too had 11 points. Yes. So that's it. I think the correct answer is 11.2. Okay, so it's just basically the same method. It's not difficult. It's not difficult at all. I'll look for more challenging questions, send them to you to try your hands on. All right. Okay, we can decide to, do we discuss this? Class, do we discuss?
Yes, sir.
So let's
Okay.
discuss it.
All right, so you are given two liquids, two immiscible liquids, and you have to find the displacement of the coin. The coin is placed under the liquid and an observer views from above, find the displacement. So generally displacement is real depth minus apparent depth. Okay, if you look at this, the total real depth will be 40 plus 8, so 48. But the question is that what will be the total apparent depth? Here you must pick it liquid by liquid. For liquid A, the apparent depth would be 8 real depth, which is 8, divided by the refractive index of liquid A, which is 1.3. For liquid B, 8 apparent depth would be 40 divided by the refractive index 1.4. So let's calculate the total apparent depth. Total apparent depth is 8 on 1.3 plus 40 on 1.4. Yasmin?
Sir, please, the refractive index, you have interchanged them.
A is 1.3. A for liquid A is 1.3. Refractive
Sir,
index of liquid B, 1.4.
sir, but liquid A is 40.
Okay, liquid A is a denser one. Okay, I've gotten your point. Okay, so B is 1.4. 1.4, and this is 1.3. Thank you for the observation. So let's total them. What will be the total apparent depth? Class, what's the total apparent depth? Hey, who is talking?
36.484.
36.84.
484.
It's 48.
Okay, 448, so 36.85 will do. Therefore, the displacement, hello?
Sir, it's 36.48, not 84.
Okay, so 36.48. All right, thank you. So the displacement will be 48 minus 36.48. And that must certainly give us the 11. Is that 22? Is that 22 point what? Or 11?
11.52.
11.52 centimeter. okay, depending on how you did your rounding up or approximation. So this is a solution to the Nigerian WASI yes paper. All right. So on Thursday we'll be looking at refraction of light in triangular prism. Triangular prism. This is another important practical bias question. Yeah, some of you watched the video on practicals and then sent me questions. I encourage the rest of you to also do same. Watch when you have issues, find a way. Okay. So Gideon, I remember you asked that the whoever did the narration said you should do the take your values twice. Gideon, is that your question?
Yeah, sir, please. They were giving like a different set of angle of incidence to
Yes.
find the angle of refraction, but then the refractive index was not given. So I was asking you have to redraw all the diagrams for the given
Sometimes,
angle.
yes, that must, you see, in our experiment, because of for precautionary sake, you take double measurements. So meaning that you must do it twice. Redraw, take your measurements. But for light experiment, we often do not adhere to that rule. This is because it will waste your time. Even for light experiment, the first one will all even waste your time. Okay. And then come to talk of doing the same thing twice. So ideally, yes, doing it twice to ensure that your values are accurate is a precautionary measure. Because of the time wasting in light experiment, we usually do not have that laxity to take double measurement. We make sure that whatever single measurement we are taking or reading is exact and precise. Because if you want to do it twice for precaution, it would certainly waste your time. You can't finish. Gideon, are you okay?
So please, I was not apart from the first angle of incidence, there were other angle of incidence that he calculated for, but then he didn't show the calculation. He just placed
I
them there.
think it's because of time and how lengthy the video would be. So he was just using the first one to guide you understand. I think I will have to find time to also do this. It will help students. Okay. So usually you are given different angles of incidence, about 5 of them. And each and every one you should draw, view through the prism, trace the images P1, P2, okay, to take measurement of your angle of refraction. Okay, but because of time, I think it is for that reason that the concentration was only on the first angle of incidence. All right, I hope you're okay.
Yes, sir. Please, thank you.
All right, so our time is up. This is there any other question?
So this is only the practicals, the reflection of light. That's the only practicals you are going to do when it comes to light, or there are other
No,
practicals
there
that you
are
do
other
attached to it.
practicals. Even in triangular prism, there are practicals. In lenses, there are practicals. So as we go through, I'll be drawing your attention to the practical application of them. Are you okay?
Okay, sir.
All right. So this is where we end today's show. I'll upload the video so that those of you who missed can have it. Until Thursday, may the good Lord be with you. Take care of yourself and bye-bye.
Bye.
Nah.
Okay, Ella.